Hello, my name is Alex, and I'm an 8th grader at Templeton, and I'm making a project this year on making a skateboard calculator, where you input numbers on the weight of a person, the weight of the board, the amount of force that you press down on, and then it'll tell you how high you can ollie. I wanted to choose this project because I love the way that people can move the board with their feet, and I wanted to take a more scientific approach to study the way that each small change can affect the whole trick. My presentation will be split up into 5 parts. You've already heard the introduction, but I will talk about how ollieing works and how modeling works, and then I'm going to talk about the tests and results of my tests, and also I'm going to conclude my presentation with a conclusion. There are 2 main parts of a skateboard. There's the truck, which these are the trucks. They house the wheels and they make it so you can roll around. And then there's the deck of the board, which is the wooden part, and it is comprised of 2 parts. It has the tail, which is the back part, and this is where you put your foot when you do an ollie. And it has the nose, which is the front foot, and you use the nose when you ollie, when you pull your foot up, so that your foot doesn't fly off. Okay, so this is a video of me trying to ollie, and basically you see him in the video, I'm pushing down, and I'm gonna jump with my weight distributed on both feet equally. And so when I'm jumping, at the very last second, what I do is I extend my ankle, and I push down on the tail, and then the tail hits the ground, and it bounces the board up. And then my front foot is sliding up the board, and it keeps sliding until it hits a little cranny right between the nose, where the nose meets the bolts of the board, and then it levels out the board, and then the board is completely level in the air, and then it comes back down. A mathematical model is a representation of a real thing. Mathematical models are useful because you can predict what will happen in certain situations without ever doing experimentation. Say you build a pressurized air rocket launcher and you wanted to predict how fast it was going. If you knew the starting speed of the rocket, you could subtract the starting speed of the rocket by gravity's speed each second, and you do that every second, and you could figure out how fast the rocket was going. You could change this into a formula that states the speed of rocket is equal to the starting speed minus gravity times the amount of seconds that have gone by. If you wanted to figure out the height, you could convert it to meters per second and add up each second the meters per second. So now the formula for height is equal to the formula for the speed of the rocket times the amount of time the rocket is spent in the air. I use this in my project. Instead of launching a rocket, I launch a human, or human jumps, and I have a few more parameters in my project, and also I have a lot more conversions, but at the core, it's the same. One of the downsides of my project is there was no way to tell if I'd actually succeeded or not in creating a program that was accurate, because there was no way to do the exact same things I'm doing in the program in real life and test the accuracy. The closest I could get to testing if my project worked was to graph the data and check to see what the graph looked like. This graph has 1,000 different data points, but all I can take away from it is that when you jump, you go up and come back down. I enjoyed this project a lot because I took the boring math and science I learned in school and I did something really fun with it. My original idea was to create an animation that went along with the calculator, but I ran out of time, so I couldn't do it. I was pretty disappointed by that, so I'm thinking I'll work on the project through the summer to finish it up. That was the end of my presentation. I hope you liked it, and thanks for watching.